start playing the game. All right. Let's see. Before we get started, I wanted to point out a thing that I noticed, which is, so there's the issue with the play, right? And Hunter has generally edited the class inside it, right, Hunter, did you, like, change the ThinkDSP file, or is this like a custom function that you wrote yourself? Hunter, wake up. I was talking to you. Hunter walked away. Let's see, it was a play _ wave. Oh no, it's right here. Yeah, so this doesn't work because, because it, like, the guy that wrote ThinkDSP uses aplay, which is, only works in Unix. So he wrote his stuff, I assume, using, it's Linux based, and so if you're doing it that way, then it doesn't work. So so you can make the changes that Hunter suggested. Also, I noticed is that it creates, when you run the play function, it will create a .wave file for you. Like, it creates a sound file, and then you can just click on that, and it'll, media player or whatever will play it. Even though it'll throw a little warning and say, I don't know what the heck aplay is, but then it still creates the .wave file. Yeah, so there's a number of reasonable workarounds. Are there any questions about? Yeah, that will also work, Edward. So we got some good stuff. But those of you who don't want to worry about it, just use Hunter's workaround, and I think I'm going to start using that too. So, Hunter, that makes up for the fact that you didn't include your ThinkDSP file in your homework assignment. We still like you. So, all right. All of that aside, are there any questions about the assignment that you just submitted a moment ago before we move on to today's class? Judging by the silence, I'll take it as no. All right. I'm going to grade those this afternoon, so we'll get those grades back to you. I anticipate the grades will be just fine as long as you honestly made a good attempt at it. You should have been able to do it. So let's see. All right, I'm going to close this for now because we're not going to worry about it. We're going to focus. We're going to go through some stuff first. Today's lecture is all about harmonics. I thought this was a really cool chapter. I learned some stuff about harmonics that I didn't know, so that was pretty fun. So let's jump in. We got to get a couple of definitions out of the way, and most importantly is we're going to look at what we call harmonic structure. Harmonic structure, which is defined as the set of sinusoids which make up a spectrum. And it turns out we can actually pretty easily come up with a mathematical sort of description of the harmonic structure that describes all of the sinusoids that fill up the spectrum. So sinusoids have a harmonic structure, or excuse me, like pure sine waves have a harmonic structure that's not very interesting. So in this class, we're going to look at, let's look at some more complex waveforms, starting with a triangle wave. Triangle wave looks like this fellow. It just sort of goes up from 1 and ramps down to -1 and ramps up to 1, back and forth. And again, notice that the ramp sort of progresses forward, right? In the assignment today, you're gonna get that's due on Friday, you'll have to make a sawtooth wave. A sawtooth wave looks sort of like a triangle wave, except when it ramps up, instead of ramping down, it just drops straight down and then ramps up again and then drops straight down and ramps up again. So here is a segment of a triangle signal that's at 200 hertz. So let's go ahead and take a look at the code for implementing our triangle wave. Let me just call this demo.py. We're going to import some things. Import matplotlib.py plot. If I can spell as PLT, and then import think DSP, and then let's go ahead and make a triangle signal. So we'll say signal equals think DSP dot triangle signal, and let's put it at 200 hertz, and let's go ahead and plot it. Signal. I haven't eaten lunch yet, man. I'm struggling. Dot plot and PLT dot show. So we got a 200 hertz triangle signal. We should basically get exactly what we saw in the textbook figure, and sure enough, that's what we get, right? So it goes from 1 to -1. We got the triangle signal. It all looks pretty good, and it's really easy to put it up there. So now let's go ahead and take a look at the spectrum, though. That's what we care about. So let's say wave equals signal.wave, signal.makeWave. Duration equals 0.5. And let's set the frame rate. He calls it the frame rate. This is the sample rate for us. And let's make it 10 kilohertz, 10,000 hertz. And let's look at the spectrum. Equals wave.make spectrum. Spectrum.plot and PLT.show. All right, so I threw out some warnings. Why did I throw out a warning? Weird. All right, so we've got this spectrum here. We've got a fundamental frequency that if I go and sort of scroll down, the sort of X thing in the bottom right corner there will tell me that it's at 200 hertz. And then we have another one at 600, and another one at 1,000, and another one at, what, like 1,400, and then so on and so forth. Now, there's two interesting observations that we make about the spectrum of the triangle wave. And the first one is that the harmonics exist not at places that we would expect them to exist. Let's come back here to our notes. Let's say there are two, I don't need to bold that, two interesting observations about the spectrum. Actually, you know, in fact, I'm going to go ahead and copy that guy so we can have it to look at. Two interesting observations about the spectrum. The first one is that the harmonics exist at odd multiples of the spectrum, or of the fundamental frequency. Right. We would expect, since our fundamental frequency is 200, we would expect 200, 400, 800, 1600, and so on and so forth, right? That's kind of the basic structure that we would expect, but we got this instead. Well, 200, 600, 1,000, 1,400, 1,800, and so on and so forth. So what we got was 200, 600, 1,000, 1,400, etc. You know, this would have been 1x, 2x, 4x, 8x, and so on. So what we mean by we got odd multiples is that of the fundamental frequency, we got 1x, and then we got 600 is times 3, so 3x. 1,000 is 5x. 1,400 is 7x. And so on and so forth. So the spectrum here, the harmonics exist at odd multiples of the fundamental frequency. 1, 3, 5, 7, 9, 11, 13, 15, all the way up. So that's the first thing, that odd multiples exist. And the second one is that the amplitude drops off at the square of the ratio of the frequency. What the heck does that mean? So if we look at the change here from the fundamental frequency to the next one, we went from 200 to 600. So that's a relationship of 200 over 600 equals 0.333 repeating, or 1/3. That's the frequency. And next up, if we go and look at the ratios of the amplitude, so this first one, well, we got to go backwards, right? So this top one was, I'm going to call it at like 2030, looking at the y-axis. And the bottom one here is at like let's see, we had what? Yeah, 2030, and then here we have like 230. So our ratio there is 230 over 2030. And that also, well, that equals 0.11, which roughly correlates to 1/9. So the amplitude was at 1/9, whereas the frequency drop-off was at 1/3. So whatever the drop-off is, that's going to be the drop-off in amplitude. So to the next one would be what? Let's see, what do we have? Well, we just keep dividing by 1/9 as we go on and go forth. So when we define, let me make this last note. We define the harmonic spectrum. We would say that for a triangle wave, the harmonics exist at odd multiples which drop off as a ratio of 1/f squared. And put that in parentheses. So if you have to give a definition for the harmonic structure, such as on the homework assignment, that's what we're looking for, right? Where do the harmonics exist? Are they at odd multiples? Or are they at even multiples? Or are they the even and the odd multiples? And what is the ratio of the frequencies that they drop off at? Are there any questions about that? Okay, all right, so let's keep going. Let's take a look at the square wave. So if we pop over to our code, let's go ahead and change our signal now. Equals think DSP dot square signal. Also at 200 hertz. I'm going to comment these out for just now. And we're going to plot the signal. You guys should all be pretty familiar with what a square wave is. Of course, you got to remove that first. And then there we go, right? There's a square wave. Let's go ahead and grab a screenshot for the notes. Pretty standard issue, right? You guys are familiar with square waves. Go ahead and add that in. Now let's go ahead and take a look at the spectrum. So I'm going to comment this out, get the wave, get the spectrum, plot the spectrum. And here we go. So here's our spectrum of our square wave. Make a copy of that for our notes. And let's make some observations about the harmonic structure. So let's blow it up. Let's look and see, first off, where our frequencies at. We have our fundamental frequencies at 200, and then we have 600, and 1,000, and 1,400, and 1,800, and 2,200. So yeah, so we've got the odd multiples again. So let's say that the harmonics of the square wave exist at the odd multiples of the fundamental frequency. And then let's talk about the amplitudes here. So we started at, let's just call it 3,200, and we dropped it down to 1,000. So we dropped off by a third, even though the frequency itself was just a third, right? So the amplitude drops off as a proportion of the frequency, not the frequency squared. Right, so we had, what, 200 over 600 gave us that, and then we had, what do we have? 1,000. What, 1,080 maybe? And 3,200, so let's say 1,080 and 3,200. You know, minus my measurement error, you can see that it's both that same proportion there, right? So it's equal to 1 over f instead of 1 over f squared. So for the square wave, we see that they're at odd multiples of the fundamental frequency, and the amplitude drops off as a proportion of the frequency, not the frequency squared. So any questions about that? All right, let's talk about your exercises, because they have to do with this. We're going to move on to a different topic, but I wanted to real quick mention what what you guys need to do in your Python exercises. 2 exercises this time. The first one is you're going to create a sawtooth. So a sawtooth signal is a waveform that ramps up from -1 to 1 and then drops to -1 and then repeats, right? And then we have a link to the Wikipedia page. So you're going to write a new Python class called Sawtooth Signal, which extends the signal class in the same way that cosignal does, and sine signal does, and triangle signal does, and square signal does. You're going to make one called Sawtooth Signal that extends the signal class and creates a sawtooth wave. And then compute and plot the spectrum of that sawtooth wave. And then how can you describe its harmonic structure? For example, we already talked about the triangle wave has odd harmonics that drop off in proportion to 1 over f squared. What is the description of the harmonic structure for the sawtooth wave? And then exercise 2 says that we already just saw that triangle waves and square waves contain odd harmonics. The triangle wave harmonic drops off in proportion to f squared. The square wave harmonics drop off in proportion to 1 over f. And when you did exercise 1, you should have found out what the harmonic structure of the the Sawtooth Wave is in exercise 1. What I want you to do now is come up with a custom signal, right? So we create a custom signal class that extends the signal class, but it needs to have a specific harmonic structure. So you need to like reverse engineer the harmonic structure, create one that has both even and odd harmonics, and that drops off in proportion to 1 over f squared, and plot the waveform and the spectrum. Are there any questions about these two exercises? Hunter asks, are any of the extensions of the DSP file that we're going to use be used in the future? Yeah, I would say so, probably. And then Edward asks, or says, when we say harmonic structure, is that equivalent to spectrum structure for non-musical analysis? Yeah, probably. We're going to call it harmonic structure for now. I don't think I've ever heard the term spectrum structure. So the musical folks have sort of co-opted the term harmonic, but it's used in other fields as well. It's not limited to just music. Bashir asks, for the fundamental frequency, what would that be? I'm not sure I understand your question, Bashir. What would what be? How would we figure out the fundamental frequency of the signal? That's up to you, right? So what the fundamental frequency is not so important to these exercises, right? You should be able to you should be able to define, and that's part of what the signal class does. But you should be able to define the fundamental frequency of your signal after the fact in the constructor. So as we'll see here in a second, you can define any fundamental frequency that you want, and then weird stuff happens. All right. Edward says, so we are basically analyzing the slope of the frequency spectrum if we interpolate different discrete impulses we have. Edward, you're way overthinking it, my man. You're not really going to look at the slope, right? Because we're considering the discrete sinusoids, right? We're not looking at the sort of spectrum as a curve, right? We're looking at it as those discrete sinusoids sitting in place, right? We're not accounting for noise yet. Noise will sort of jack up everything, right? Right now we're just looking at a sort of ideal case. So what I would do for exercise 2 would be to kind of work my way backwards, right? I would sort of build my spectrum and then kind of do the reverse to sort of see how, see what signal comes out the other end, right? I would look at the ThinkDSP sort of spectrum class, see how that's constructed, and then create my own custom spectrum that had met those requirements, and then kind of went from there to see what the waveform looked like. So there's a couple of different approaches to solving this one, but both of them are going to require sort of taking a look at the code itself, which I think is a pretty good exercise. All right, any other questions before we move on? All right, so the next bit is pretty cool, not directly relevant to your assignments, but it will kind of make its way in there, and we're also going to see why I really love the new direction we're taking the course, right? So we're going to talk about aliasing. And we're going to take a look at what it means to actually do aliasing. We, earlier in the class, kind of talked about it in a mathematical sense, right? Stuff gets messed up if you go over a specific frequency. But let's take a look. And let's start by kind of asking this question, right? You know, if we go back and look at the code, that we wrote, we saw that we set our frame rate to 10 kilohertz, right? 10,000 hertz, and we were sampling a signal at 200 hertz. So let's say we were looking at a spectrum with a fundamental frequency of 200 hertz, sampled at a rate of 10,000 hertz. What would happen if we increased, I was going to say like cranked up, but that's not very professional. If we increased the fundamental frequency to, let's call it 1.1 kilohertz, right? Or 1,100 hertz. So first off, what would we expect to see, right? Let's forget, I know we already kind of know that aliasing exists, and we know that kind of weird stuff is going to happen, but when we create this signal, let's do the triangle wave. You know, what will of the triangle wave be? What would we expect to see based on what we know already? I'm just getting ahead of Edward telling us what the correct answer is. So we would expect to see odd harmonics, you know, falling off at 1 over f squared, right? So we would sort of expect this, a fundamental at 1,100 hertz, and amplitude, let's just call it 1. And then we want to see a harmonic at what? 3,300 hertz, and amplitude equals 1/9. And then a harmonic at 5,500 hertz at an amplitude equals 1/25. And then a harmonic at what? 7,700 hertz at an amplitude that is 1/49th, right? This is what we expect, right? Now that we kind of know how to describe the spectrum of the signals that we're working with, we can predict what we're going to get in advance, right? This is what the spectrum should look like, right? The harmonics are going to play out this way, and they're going to occur at those frequencies. But as you can probably guess, because we've gone out of our way to say that, that's probably not what's going to happen. So let's go ahead and take a look at our, not the square signal, although that would work as well, but let's take a look at the triangle signal at 1,100 hertz. We're going to crank up the frequency and take a look at the spectrum. And of course, I got to get rid of that. So, well, that's not what we got, was it? We got some trash. Let's see. Well, we've got a fundamental, a clear fundamental at 1,100. That would be expected. We've also got another one at what, 33,300. So that's kind of what we expect. And then we've got another one at 4,500. Should be at 5,500. And then, of course, we've also got, if I zoom in, we got all these other little harmonics hanging out and doing weird stuff. So, let me get a better image of that again. What is causing all that mess? Let's go ahead and save that for our notes. So let's say what we got was that. So the fundamental frequency is at 1100 hertz as expected. The first harmonic at 3300 hertz is present as well. And then this is where it goes off the rails, right? The next one down occurs at 4500. Second harmonic should be at 5500 hertz, is at 4500 hertz. What is going on? So what is causing that to happen? And then of course the other guys are showing up in other places. We can also look and see sort of the next one, and we can call them the next one because we know we're going down in size. So if we kind of make our way down, the next one, which should be at 77, is actually at 2300. The next one that should be at 9900 is actually at just 100 hertz. So we got all kinds of weird stuff going on. And it turns out that aliasing is what causes this. Let's take a look at the signal. Let me close this. Let's create a new one. I'm just going to call it aliasing.py. I'm going to import some of our stuff. Frame rate equals 10,000. And let's go ahead and just create a cosine signal. So cosignal equals think dsp.cosignal at, I'm going to do this one at, well, let's start at 200 hertz and we'll kind of work our way through. At a duration equals the signal dot period times 5. So we only want to see like a specific part because we only want to look at the segment. Segment equals signal dot make wave. Duration equals duration, and frame rate equals frame rate. Segment dot plot and plt dot show. So we plot that the first time, we get a pretty nice 200 hertz, really clean sinusoid. But what happens? Let me do this. Did he give us a scatter function? Let's see. Nope, he didn't. Just a plot. Okay. All right. Let's crank up the frequency. Let's make it 400 hertz. Now, it still looks like a pretty good sine wave, but there's some, you can see some roughness, right? It's not quite as clean as it was. If I crank it up to 800 hertz. Now it's really starting to get choppy, right? We're starting to lose some of that frequency information, right? Let's go to like 2000 hertz. Bam, now it's really starting to look like a mess. Now what happens is if I go all the way to 5000 hertz, which is half of our frame rate, half of our sample rate, here's what we're going to get. We basically get a triangle wave again, right? Because all we're getting is just the tops and bottoms of the cosine signal, right? So we end up getting this sort of triangle wave. But really, we're only sampling just there and there and there and there. And what gets interesting is if we move away in either direction. So let's go ahead and say like 4500. It's going to look like that. Let's save that because we need to make another one. So let's put that in our notes. Let's make a note. 4500 hertz cosine signal. And if we change it to 5500, it gets kind of chopped off, but if you look at the part up to 800, or excuse me, 0.008, it's exactly the same, right? It's the same signal. So what that means is, as we move away from that center point, that 5,000 hertz, the signal looks the same in either direction, right? So what that leads to is 5,500 hertz should have been our next harmonic, right? But it looks the same at a 10,000 hertz sample rate or frame rate. It looks the same as a 4,500 hertz cosine signal. The system cannot tell the difference between the two. And so what that leads to is it leads to the signal doing what's called folding back on itself, or the spectrum folds back on itself. And we can kind of mess around and see what's going on. If we go back to our original signal here, 1100, let's take a look. Let's run that after I get rid of that. I'm kind of zoom in here. And so sure enough, the third harmonic, the next biggest one, should have been at 5,500, but is in fact at 4,500, right? So instead of, it basically hit the 5,000 hertz barrier and then just bounced back. It got reflected back over here. And we can kind of see that play out as we kind of look through the spectrum. So what should the next harmonic have been? The next harmonic ought to have been at, so let's see, the fourth harmonic should have been at where? At 7,700 hertz. So now we can kind of predict where it will show up, because now we know that, let's do this, at a frame, here's the important thing, here's the test question, at a frame rate actually, let me do it this way. So what we call the folding frequency, the frequency at which the higher frequency harmonics are folded back into the lower frequencies of the spectrum. You know this by a different name. It is also known as the Nyquist frequency. And it's always equal to, so the folding frequency, or folding slash Nyquist frequency is always equal to 1/2 times the frame rate, or the sample frequency. And basically that tells us that you can't go past whatever our frame rate is. Notice that like the plot even knew this ahead of time, right? The furthest out it goes is 5,000, right? Half of the sample frequency. So the spectrum cannot exist at more than half of the sample frequency. We're limited to this box. And basically the rest of the spectrum just sort of bounces back around inside this. So let's go back to here where it should have been at 770 hertz. Instead, let's see what the difference is. 770 minus 5,000 equals 2,700. and 5,000. So it should have gone 2,700 hertz past 5,000, but means it's going to fold back to 2,300. So say this is where the aliased harmonic will be. And let's take a look at our spectrum. And sure enough, our third harmonic is right there at 2,300 hertz. Let's do the next one. The next one should have been, let's see, the fifth harmonic should have been at 9,900 hertz. But 9,900 minus 5,000 is equal to 4,900, and 5,000 minus 4,900 is equal to 100. So now instead, the fifth harmonic shows up at 100 hertz. So it gets folded back, the spectrum folds back across the frequency. All right, any questions about that? So that is, in a more practical way, what is aliasing, right? Think of the spectrum harmonics as getting reflected. They want to be progressing out according to their multiples, but they hit that folding frequency and they get folded back around based on what the distance between them and the folding frequency is. And that kind of just gets reflected back around. So they'll bounce in. So for example, the next one would be the sixth harmonic. Should have been at what? 7, 9, 11. So what? 121. 12,100 hertz. I think that's correct. So 12,100 minus 5,000 gets us 7,100. And then 7,100 minus 5,000 is going to get us 2,100. So we would expect to see the next harmonic at 2,100. So 1, 2, 3, 4, 5. The next one is going to be this. That sure enough is at 2,100 hertz. So you can, those spectrum sinusoids, those harmonics are just sort of ricocheting around inside the window from 0 to 5,000. All right. So any questions about aliasing, or how to describe the spectrum and how to predict where the aliased harmonic would be? So you might expect a exam question that looks something like this. Let's say a signal is sampled at a frame rate of, I don't know, let's call it 12,000 hertz. If the fundamental frequency is 750, I'm just making this stuff up, 750 hertz, where will, let's see, well, actually we need to know the characteristics, right? So let's say a square wave is sampled at a frame rate of 12,000 hertz. The fundamental frequency is 750 hertz. Where will the fourth harmonic appear in the spectrum? That's going to be an awesome exam question, or a sample of an exam question. So let's go ahead and, we got like 4 minutes left. So what would we expect? So the square wave harmonics occur at odd multiples. So we would expect what? 750 times 3. So let's do this. 1 times 750 equals 750. Then 3 times 750 equals that. 5, we're interested in the fourth harmonic, so the third harmonic would be 5 times 750 equals that. The fourth harmonic will be times 7. 7 times 750. So the harmonic will appear, should be at 5200. No, look at that. I didn't do very good. So if the frame rate is 12 hertz, so 0.5 times 12,000 equals 6,000. So actually, by the way I've done this question, the fourth harmonic will appear at 5,250 because it's inside the folding frequency. It's inside the Nyquist frequency. So let's change this. Where will the sixth harmonic appear? So that'd be 9 times 750. There's our fifth harmonic. 11 times 750 equals that. There we go. So now, so 1, 2, 3, 4, 5. Oop. First, second, third, fourth, fifth. Let's do one more. Which means actually I got that one wrong. 13 times 750. That's what I get for making it up as I go. All right. So the first harmonic, or the sixth harmonic there, is at 9,750 hertz. 9,750 minus 6,000 equals 3,750, and 6,000 minus 3,750 equals 2,200. So well, I miscounted because this one is the fundamental, the first one, which makes this one the first harmonic, the second, the third, the fourth, the fifth, and the sixth. I made the same mistake too when I did it just now. But yeah, that's the sixth harmonic. So we would say that the sixth harmonic of the spectrum will appear at 2,025 hertz. All right, so any questions about that? Cool. Well, that is all that we have time for today. So don't forget, you've got another exercise that's due Friday, and we'll pick up with chapter 3 from the Think DSP textbook on Friday. So thank you so much, guys. I'll see you next time.